The National Electrical Code, or NEC Table 310.16, provides correction factors for ambient temperatures up to 40 degrees Celsius or 104 degrees Fahrenheit. These correction factors are used to adjust the ampacity of conductors based on the ambient temperature in which they are installed. The correction factors are based on the assumption that the rated ampacity of the conductor is for an ambient temperature of 30 degrees Celsius or 86 degrees Fahrenheit. At higher ambient temperatures, the conductor's ampacity is reduced because of increased resistance due to thermal expansion. For THHN conductors, the correction factor is 1.4 for ambient temperatures between 21 and 25 degrees Celsius or 70 to 77 degrees Fahrenheit. For other types of conductors such as THHW, the correction factor is 1.5 for ambient temperatures between 21 and 25 degrees Celsius or 70 to 77 degrees Fahrenheit. To apply the correction factor, you multiply the conductor's rated ampacity by the factor. For example, if the rated ampacity of a THHN conductor is 100 amps and the ambient temperature is 24 degrees Celsius or 75 degrees Fahrenheit, the corrected ampacity is calculated as follows. Corrected ampacity equals 100 amps times 1.4, which equals 104 amps. It is appropriate to use the correction factors in Table 310.16 for ambient temperatures up to 25 degrees Celsius or 77 degrees Fahrenheit, considering the conductor type. This ensures that the conductors are not overloaded and operate safely within the intended design parameters. To elaborate further on the application of ampacity correction factors per NEC Table 310.16, several key considerations are important. Firstly, it is essential to accurately determine the ambient temperature in the area where the conductors are installed. The NEC defines ambient temperature as the temperature of the area immediately surrounding the conductors. This temperature can be affected by various factors, including sunlight, proximity to heat-generating equipment, and ventilation. Secondly, it is crucial to identify the correct conductor type and its corresponding temperature rating. Different conductor types have different temperature ratings, which affect their ampacity. For instance, THHN conductors are typically rated for 90 degrees Celsius or 194 degrees Fahrenheit in dry locations, while XHHW conductors are rated for 90 degrees Celsius or 194 degrees Fahrenheit in both wet and dry locations. Thirdly, when applying the correction factors, it is important to use the appropriate factor for the specific temperature range. Table 310.16 provides correction factors for various temperature ranges, and it is essential to select the correct factor based on the actual ambient temperature. Furthermore, it is important to note that correction factors are cumulative. If multiple factors affect the ampacity of a conductor, such as ambient temperature and the number of conductors in a raceway, all applicable correction factors must be applied. The NEC provides specific guidelines for rating conductors in various conditions. In addition to ambient temperature correction factors, NEC Table 310.15b3 provides adjustment factors for the number of current-carrying conductors in a raceway or cable. When the number of current-carrying conductors exceeds 3, the ampacity of each conductor must be reduced to account for the increased heat generated within the raceway or cable. The adjustment factors vary depending on the number of conductors and the insulation type. For example, if there are 4 to 6 current-carrying conductors in a raceway, the ampacity of each conductor must be reduced to 80% of its rated value for conductors with a 90 degrees Celsius insulation rating. Moreover, it's important to consider voltage drop when determining conductor size. Voltage drop occurs when the voltage at the load end of a circuit is less than the voltage at the source end. Excessive voltage drop can cause equipment to malfunction and can also lead to overheating of conductors. The NEC recommends limiting voltage drop to no more than 5% for feeders and 3% for branch circuits. To calculate voltage drop, you can use the following formula. Voltage drop equals 2 times K times I times D divided by Cm, where K is the direct current constant, which represents the resistance of a 1 foot length of conductor with a cross-sectional area of 1 circular mil. I is the current in amps. D is the one-way distance of the circuit in feet. cm is the circular mil area of the conductor. The value of K varies depending on the conductor material. For copper, K is typically 12.9 ohms per circular mil-foot. For aluminum, K is typically 21.2 ohms per circular mil-foot. To minimize voltage drop, you can increase the conductor size, reduce the circuit length, or reduce the load current. Additionally, proper overcurrent protection is crucial for ensuring the safety of electrical circuits. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors from overheating and potential fire hazards. The NEC requires that overcurrent protection devices be sized to protect conductors in accordance with their ampacity. The overcurrent protection device should not exceed the conductor's ampacity after applying all applicable correction and adjustment factors. Furthermore, it is essential to ensure that all electrical installations comply with all applicable codes and standards. The NEC is the most widely adopted electrical code in the United States, and it provides comprehensive guidelines for the safe installation and operation of electrical systems. Local jurisdictions may also have additional requirements that must be followed. Regular inspections and maintenance are essential for ensuring the ongoing safety and reliability of electrical systems. Electrical systems should be inspected regularly to identify any potential hazards, such as damaged conductors, loose connections, and overloaded circuits. Maintenance should be performed as needed to correct any deficiencies and prevent future problems. In summary, the correct application of ampacity correction factors per NEC Table 310.16 is crucial for ensuring the safe and reliable operation of electrical systems. By accurately determining the ambient temperature, selecting the correct conductor type, applying the appropriate correction factors, and considering other factors such as voltage drop and overcurrent protection, you can ensure that conductors are not overloaded and that electrical systems operate safely within their intended design parameters. These considerations are further refined by understanding the different insulation types and their suitability for various environmental conditions. For example, THHN insulation is heat-resistant and nylon-coated, providing good protection against abrasion and chemicals, making it suitable for dry locations. XHHW insulation, on the other hand, is cross-linked polyethylene, which offers excellent moisture and heat resistance, making it suitable for both wet and dry locations. The choice of insulation type can significantly impact the ampacity and longevity of the conductor, especially in harsh environments. Moreover, the installation methods also play a critical role in determining the ampacity of conductors. The NEC specifies different installation methods and their corresponding ampacity ratings. For instance, conductors installed in free air have a higher ampacity than conductors installed in conduit or cable trays, as free air allows for better heat dissipation. The installation method must be carefully considered to ensure that the conductors can operate safely without exceeding their temperature ratings. Another important aspect is the proper termination of conductors. Loose or corroded connections can increase resistance, leading to overheating and potential fire hazards. All connections must be made using appropriate connectors and tightened to the manufacturer's specifications. Regular inspection and maintenance of connections are essential to ensure their integrity and prevent future problems. Additionally, the NEC provides guidelines for grounding and bonding of electrical systems. Grounding and bonding are essential for preventing electrical shock hazards and ensuring the proper operation of overcurrent protection devices. All metallic enclosures, raceways, and equipment must be properly grounded and bonded to provide a low impedance path for fault current to return to the source. This helps to quickly trip over current protection devices and prevent electrical shock hazards. Furthermore, surge protection is an important consideration for protecting electrical equipment from voltage surges caused by lightning or other transient event. Surge protection devices, or SPDs, are designed to divert surge current away from sensitive electronic equipment and protect them from damage. The NEC provides guidelines for the installation and location of SPD to ensure their effectiveness. In addition to the NEC, other standards and guidelines may apply to electrical installations depending on the specific application and location. These may include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, the National Fire Protection Association, or NFPA, and Underwriters Laboratories, or UL. It is important to be familiar with all applicable codes and standards to ensure that electrical installations are safe and compliant. Continuing education and training are essential for staying up to date with the latest electrical codes and standards. The electrical industry is constantly evolving, with new technologies and regulations being introduced regularly. Electrical professionals should participate in continuing education courses and training programs to enhance their knowledge and skills and maintain their competency. In conclusion, the safe and reliable operation of electrical systems requires a thorough understanding of ampacity correction factors, conductor types, installation methods, termination techniques, branding and bonding, surge protection, and applicable codes and standards. By adhering to these guidelines and best practices, electrical professionals can ensure that electrical installations are safe, compliant, and efficient. And by paying close attention to detail and maintaining a commitment to safety, we can all contribute to a safer and more reliable electrical infrastructure. Remember that the information provided here is for general guidance only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer or other professional before making any decisions about electrical installations or modifications. It is also important to note that the NEC is updated every 3 years, so it is essential to use the latest edition of the code. The NEC is available for purchase from the NFPA and other sources. In addition to the technical aspects of electrical installations, it is also important to consider the human factors. The electrical work can be dangerous, and it is essential to take appropriate precautions to protect yourself and others from electrical hazards. Always wear appropriate personal protective equipment, or PPE, such as safety glasses, gloves, and insulated tools. Follow lockout/tagout procedures to de-energize circuits before working on them. And never work alone on electrical equipment. Always have someone nearby who can assist you in case of an emergency. By following these safety precautions, you can minimize the risk of electrical accidents and injuries. Electrical safety is everyone's responsibility, and it is essential to take it seriously. With proper planning, training, and adherence to safety guidelines, we can all work safely and prevent electrical accidents. And in all electrical work, remember to double-check your calculations and measurements before proceeding. A small mistake can have serious consequences, so it is essential to be accurate and thorough. Take your time, pay attention to detail, and always prioritize safety. By doing so, you can ensure that your electrical work is safe, reliable, and compliant with all applicable codes and standards. Finally, remember that electrical work is a skilled trade that requires years of training and experience. If you are not a qualified electrical professional, do not attempt to perform electrical work yourself. Hire a licensed electrician to perform any electrical work that you are not qualified to do. This will ensure that the work is done safely and correctly and that your electrical system is in good working order. Electrical safety is not something to take lightly, and it is always best to err on the side of caution. By hiring a qualified electrician, you can have peace of mind knowing that your electrical system is safe and reliable. Remember that while average temperatures provide a general guideline, actual ambient temperatures can fluctuate significantly depending on local conditions and time of day. Therefore, it is always best to measure the actual ambient temperature at the installation location to ensure accurate ampacity calculations. This is especially important in enclosed spaces or areas with poor ventilation, where temperatures can be significantly higher than the average ambient temperature. And by taking the time to accurately measure the ambient temperature and apply the appropriate correction factors, you can ensure that your electrical installations are safe and reliable, even in challenging environments. In summary, applying ampacity correction factors from NEC Table 310.16 correctly is vital for electrical safety. Accurate temperature assessment, consideration of conductor type and insulation, and adherence to NEC guidelines will help prevent overloading and ensure optimal electrical system performance.